Okay, so I'm going to go over the solutions to quiz 2. Here are my solutions. First question was a person walks 20 meters 20 degrees north of east, then walks 30 meters due south, and finally walks 20 meters 20 degrees north of west. Draw accurate graphical vectors using a protractor and a metric ruler, and assuming 1 centimeter is equivalent to 5 meters. And so based on this scaling, I used my protractor, to measure 20 degrees up from the positive x-axis, and to measure 4 centimeters along here, which equates to the 20 meters. So this in other words equates to 20 meters. And then um, 6 centimeters down this way, which equates to 30 meters, and that's due south, of course. And then 4 centimeters again, which equates to 20 meters, back 20 degrees north of west, as you see here. And then the displacement which gets the person back to the starting point is this d4 vector, which you will note is due north, as measured by the protractor, and pretty clear visibly. And so if I take a metric ruler and measure this, that comes out to be 3.2 centimeters when I did it, and that 3.2 centimeters scales to 16 meters. And so that's my graphical solution, is 16 meters due north, as I say here. Okay, so the next thing to do is to do the same problem analytically. And so to do that, I use the I hat j hat vector formalism to represent d1. So d1 vector is 20 meters cosine of 20 I hat plus 20 meters sine of 20 j hat, which is 18.8 meters I hat plus 6.8 meters j hat. d2 is minus 30 meters j hat. That's this due south vector. And then d3 is minus 20 meters cosine 20 I hat plus 20 meters sine 20 j hat, which is minus 18.8 I hat plus 6.8 meters j hat. So d1 plus d2 plus d3 is 0. This plus this plus this is 0 I hat minus 16.4 meters j hat. And d1 plus d2 plus d3 plus d4 equals 0, because all of these 4 vectors add back to getting the person to the starting point, which equates to 0 displacement. And if you solve this for d4, you get d4 is minus the quantity d1 plus d2 plus d3, which in other words is 16.4 meters j hat. All right, so I get 16 meters due north with a graphical solution, and 16.4 meters due north with the analytic solution. So the next thing to do was to compute the percent relative error, and so the graphical solution was a little bit below the analytic solution. So it's going to be negative, and it turns out to be minus 2.4%. And so your numbers are probably slightly different, not the analytic. The analytic should be the same. Your graphical vector solution is probably slightly different, and so your percent relative error would also be different. Okay, question 2 says, given 2 forces, F1 and F2, each of 2 newtons, find the maximum and minimum magnitude of the third force F3, magnitude and direction, that can be balanced with F1 and F2. In other words, so that F1 vector plus F2 vector plus F3 vector is equal to 0, just like a force table scenario. For each of your answers, draw a vector diagram showing the direction of all 3 forces. State any assumptions you are making. Be practical. Okay, so first of all, F3 can be in magnitude as small as 0, in which case F1 and F2 would just hang on opposite sides 180 degrees from each other on the force table. And so F3 is the minimum value of 0 is the minimum value for F3. Okay, to find the maximum value of F3, we um, can visualize F3 being diametrically opposed to F1 and F2, put as close together as possible. And so my solution incorporated using two separate clamps and two pulleys, one for F1 and one for F2. And in that case, you can't, practically speaking, set theta equal to 0. And so it turns out, if you actually look at the geometry and the size of the force tables that we used, that theta minimum is about 1.5 degrees if you do some simple math. And based on that, and this picture right here, F3 max would be, according to this picture, 2 times F1. F1 would represent the magnitude of either F1 or F2. Either one is 2 newtons, times the cosine of theta min. And so the F1 times the cosine of theta min would be the x component of either one of these two other balancing vectors. And so if you put 1.5 meters, degrees in for the angle, it's pretty nearly 4 newtons. It's something like 3.99. So I'm going to say that's 4. That is it.